Hi everyone, happy to be here. Today I'm going to introduce cluster serving to you. Cluster serving is distributed and automatic model inference on big data streaming frameworks, and it is based on open source project Analytics Zoo. So its full name is Analytics Zoo Cluster Serving. And now I'm going to introduce the main contents of today's presentation. Today, our contents will be divided into four sections. The first is the challenges that AI productions are facing nowadays. And then the second section is the integrated big data and AI pipeline, which is our solution to the first section, the challenges. Then I'm going to introduce the scalable online serving, which is the main topic of today to you. And after that, finally, I'm going to introduce some cross-industry end-to-end use cases. So now let's go to the first section, the challenges AI productions are facing. First, let's take a look at this diagram, which many of you may have seen before. It describes the relationship between the amount of data and the performance of machine learning. We could see that the models are divided into four categories in this diagram: the traditional learning algorithms, small neural networks, medium one, and the large neural networks. We could see as the amount of data increase, the performance of all these models will all increase, but among them, the traditional learning algorithm increased to a relatively small extent, while the large neural networks increased to a large extent, which could draw a conclusion that in order to achieve the best performance as best as we can, we should first increase the scale of the neural networks, and then we also need a large amount of data, which is to say that the big data is closely related to the model performance. Then let's take a look at this diagram. In this diagram, we could see that there are many blocks. That the square of these blocks describe the amount of the code that it describes. For example, like configuration, data collection, data verification. They are all the operations and the code pieces we need to do in order to accomplish a machine learning application. And among all these blocks, we could see that in the middle, it's a small piece of machine learning code, which is to say, even if we have accomplished our machine learning code, we still have a lot of other things to do to integrate it with it that could make our machine learning pipelines work. So this is also a great challenges that we want to build our machine learning application. So the second, I'm going to introduce the integrated big data and AI pipeline. So we have posted the challenges before. So how do we solve this challenge? The answer is in this slide, integrated big data, analytics, and AI. We could see in this slide in the middle is the production AI pipeline. And from the left to the right, the prototype on laptop using sample data and to the production environment. This is the integrated big data and AI pipeline. It has four features, and they are also its advantages. The first one is easily prototype end-to-end pipelines that apply AI models to big data, which is to say that we can prototype our pipeline on the laptop, which is very convenient. And the second one is the one, zero code change from laptop to distributed cluster and seamlessly deployed on production and Hadoop Kubernetes clusters. This is to say that once we have finished our code on the laptop, we do not need to any change of the code that we could deploy it on the cluster, which is our production environment. And the last one is automate the process of applying machine learning to big data. This is to say we could make our process automatic and like a data stream, and we could make it in a workflow that it could continuously running. Then I'm going to introduce the AI frameworks on big data. On the left side is Big Deal, which is our previous project, and it is a distributed and high-performance deep learning framework based on Apache Spark. And on the right side is Analytics Zoo, which we are currently working on. It is a unified analytics plus AI platform for TensorFlow, PyTorch, Keras, Big Deal, OpenVINO, Ray, and Apache Spark. equals seamlessly scaling from the laptop to distributed big data clusters. So now I'm going to make a brief introduction to our Analytics Zoo, Unified Data Analytics and AI platform. We could see from the lowest level to the top, there are some deep learning frameworks like TensorFlow, PyTorch, OpenVINO, and also we have some also existed distributed big data frameworks like Spark, Flink, and Ray, and also some Python libraries. We could deploy them on any of the environments, like the laptop, Kubernetes cluster, Hadoop clusters, and the cloud. Above it, to integrate this lower level of libraries, we have 4 end-to-end pipelines: distributed TensorFlow, PyTorch on Spark, Ray on Spark, Spark data frame machine learning pipelines for deep learning, and inference model. And above it, we have 2 big categories of machine learning workflow: auto machine learning and automatic cluster serving, which is our topic, and we will describe in detail later. Also, except them, we have some out-of-box models and algorithms like recommendation, time series, computer vision, and natural language processing. Users could directly use it once they have installed Analytics Zoo. So now the third section, I'm going to introduce the scalable online serving. First, what is serving? Let's first introduce the concept. Serving is once we have a model and input data. The input data will do the pre-processing, and then it will go to the model. The model will do the inference based on its weight and bias, and then it will do the pre-processing and generates the result. So the process of the input data and this whole workflow and get the result, this is serving. So this slide is an example of the classical web serving. From the bottom, it's a model service loader. It will load the service bundle and the model file. And then it will load some model services of the different model version. And the model services will go to the model service string and then give the message and data to the model service manager. Then on the left side, we have a user. The user will call this service by a REST or a gRPC API. And then it will go to the request will go to the model service manager, and the model service manager will give the correct version of the model, and it will do the inference and send the result back as the response to the user. Okay, and now this is the abstract concept of the distributed model serving. Once we have a serving, and then we have a data source, we could have a lot of nodes in the cluster, and the data would flow into the clusters and have many levels. In each level, we could do our custom operations. Also, on each node, we could deploy our Analytics Zoo model, which could parallelize the pipeline and have a great scalability. And also, the whole workflow could be integrated with each of the big data frameworks like the Flink and Spark. And now this is the architecture of the main version of cluster serving. On the left side is Redis. It contains the input data pipeline and the output data pipeline. Note that they are two different concepts, although they are located in the same memory space on the computer. And then once the data go into the input pipeline, it will go into the right side, the PageFlink cluster. The job manager will schedule the task and give them to the task manager. The data will be taken by the task manager and will go to the data source and inference model and data sink. Data source will get the input data, and then it will go to the inference model to do the inference. Inference model is a lower level module in Analytics Zoo. And then after it gets the result of the inference, it will go to the data sink and then write back to the result in Redis in a distributed manner. And also we have supported the cluster serving based on the Spark streaming version. So now I'm going to introduce some main advantages of analytic zoo cluster serving. First, the ease of deployment. We will publish the existing Docker image, and the one container will contain all the dependencies that are needed. And also, they could be leveraged on the existing Yang or Kubernetes cluster. The second one is wide range deep learning model support. Analytic zoo cluster serving could support models of TensorFlow, Caffe, OpenVINO, PyTorch, and BigDeal. Regardless of what kind of version it is, it will load the model automatically according to the model type. A third one is low latency. Our main version of cluster serving is based on Apache Flink, which is a continuous streaming pipeline. And also Spark version is also supported. It has the very low latency. And the last one is high throughput and scalability. First, we have some optimization of the multi-thread control at the lowest level. And also, as we mentioned before, in the distributed model serving, that we could easily scale out to clusters and take advantages of the big data frameworks. Then I'm going to introduce the API from the user's perspective. First, on the right side is a Hadoop or Yang or the Kubernetes cluster. It is located in the local node or the Docker container. On the left side, there are two users. The upper one is the HTTP request that is used by the HTTP API user. The user will send the HTTP request to the server, and the server will send it to the container. And the model in the container will do the inference and send the result back to the server. And the HTTP front-end server will do some control, and then it will send the response back to the user. On the downside is a Python PubSub user. It will have two Python APIs. One is the input queue for the request to push the data in the container, and one is the output queue to get the data out of the container. And user could use these two APIs to push and get the data. And after that, here is the cluster serving workflow overview. This describes some basic steps to start the cluster serving. First, user should install and prepare the cluster serving environment on local node. And then once the environment is ready, user could launch the cluster serving service. And then user could use the two APIs described just now to do the distributed and the real-time inference. Here is a very quick start to start the cluster serving. First, to start the Docker container, you could just run a single command, docker run, to get our published images. The second step is log into the container. And then once user is in the container, it will have all the dependencies that the cluster serving needs. And user could just run a very simple command, cluster serving start. It is a bash command that could start the cluster serving. Once user have started the cluster serving, it could include the data into the pipeline and start the inference. So now user will use the API to include the data. Here we provide two types of APIs, HTTP Sync API and the PubSub Python API. The HTTP Sync API is the API run in sync manner. The request will be block waiting until it gets a response. And also, this API is compatible with TF serving. And the second one is Python PubSub Async API. It runs in async manner, and user could get the result anytime once they include the data. Now let's take a look at the API, HTTP API. First, we could see that the HTTP API supports scalars, tensors, sparse tensors, image encodings. These all kinds of data types. And we could take a look at the right side, these images. It describes that all these kind of data could be described in a JSON format. And we could take this as a request to give it to cluster serving. Then let's take a look at the PubSub API of Python. Also, it supports all the kind of APIs that the HTTP API supports just now. But the difference now is that it needs an input queue object that, and also the tensor are described in the NumPy array. And here we could see in the example, we have generate two tensors by NumPy module, and then we use an input queue object to enqueue our data. So finally, I'm going to share some cross-industry end-to-end use cases to you. First is a garbage classification on Tianchi competition. This is the garbage classification task. At first, we have the training data and the pre-trained model of TensorFlow. But this model may not be very good, and maybe performance is not so well on the realistic data. And then we need some transfer learning to improve our model. After that, once we got a fine-tuned model, and we could use our testing data and a fine-tuned model to start the inference. We have a patch Flink cluster, and on each node, we use analytic zoo to load the model and deploy the model on the executor. Then we could do the pre-processing and inference on each executor. This could accelerate the classification task to a great extent. And finally, it's a medical image analysis. This is also a project that similar to one of our previous projects. In medical aspect, the raw image is usually very big, and it will be cut into many pieces, sometimes thousands or 10,000s, to do the further analysis. Then each small image need to do the pre-processing, predict, and post-processing, and get an overall result. From our current experience, the bottlenecks are usually at the pre-processing and inference task. This could add to 1 to 2 hours per large piece of image. And with analytic zoo distributed serving, we could accelerate it into the minutes. So after that, we have finished all of the sharing of our today's cluster serving. And thank you.